second tutorial is by
So, hi.
Okay, so again, this tutorial is going to be getting practice with some of the tools and techniques that Carolyn taught us about, but trying to do it in a setting where we're getting to learn something new. And let me restate the rule of last tutorial. All questions are encouraged, especially questions that field theorists have when they're very confused about lattices. So we're going to talk about two things, and they're related to one another. That is condensation defects and higher gauging. And let's recall how in lecture 2 from Carolyn, we saw that there's a machine to build topological orders. I start off with, in 2 plus 1D, a zero form SPT. And if I gauge the symmetry protecting the SPT, I can get a 2 plus 1D topological order. So Carolyn showed a few examples, one of which will be the one that our case study of this tutorial will be based around. Which is 2 plus 1D Z2 gauge theory. And in this tutorial, we'll always be on a square lattice. I'll call it lambda. So let's recall in this example, how did it work? Well, I started off with a paramagnet. So the Hilbert space was a bunch of qubits on the sites S of the square lattice. The Hamiltonian of the paramagnet was the sum over all the Pauli operators X acting on each site. And then we gauged a Z2 symmetry, which is generated by the spin flip operator. It's clearly commutative with this Hamiltonian. And we get some new model with a new Hilbert space. So in this case, now we have qubits on the edges of the square lattice. The edge is E. And Carolyn energetically enforced this flatness condition. Here I'll enforce it at the level of the Hilbert space. And we have this Hamiltonian, which was the star term. Just as a reminder, EP is a plaquette operator, which is a product of Z's on the edges bounding a plaquette, and AS is the star operator, which is a product of X operators that all touch this site. Okay. So now, to come across condensation defects, I want to ask a slightly different question. What if instead of gauging a zero form SPT without any defects, I insert a defect, and then I gauge the SPT with the defect inserted? What do I get? And I should get a topological order with the defect. Yes, there's a question.
What's the definition of SPT and topological order?
Oh, so that's something Carolyn reviewed in her first lectures. I don't want to go through all of it, but roughly speaking, I would say an SPT is, here's one definition. An SPT is a gapped phase with a unique ground state, and it has symmetries. A topological order, you could define it as a phase where you have some higher form symmetries and it's spontaneously broken. But yeah, we can talk more about it after, but that's a whole nother lecture. So. Okay. Good, so let's insert a defect that I don't think we've seen yet at this school. So I want to insert what I'll call a Z2 SSB defect. So this is going to be a defect where the Z2 symmetry of this paramagnet is spontaneously broken in this localized codimension 1 subspace. So we're going to insert this Z2 SSB defect at the line where x is equal to 0 on the square lattice. So I have my square lattice, and I have some line where x is equal to 0, and I want the Z2 symmetry to be spontaneously broken everywhere on this line, all the way off to infinity and minus infinity. And let me propose to you what the Hamiltonian is with this defect inserted. it should be the paramagnet Hamiltonian. And then what I'm going to do is I'm going to sum over all the lattice sites along this line. I'll remove the poly X operator from the paramagnet Hamiltonian, and then I'll replace it with an Ising-like interaction. Good. So does that make sense? And let's see that does what I wanted to do. Well, for one, this still commutes with my symmetry operator. So that's good. If I insert a defect, that's supposed to spontaneously break the symmetry. I don't want to explicitly break the symmetry in the process, so that's a good check. Another thing you can check is this Hamiltonian. It's exactly solvable, and it has two ground states now. It's a gapped Hamiltonian now with two ground states. And they're going to be ground states where every qubit that does not have x equals 0 has the position x equals 0 has the poly x operator equaling 1, and for all the qubits along this line, the product of z's are equal to 1. So there's two ground states. I'll call them GS1, 2. You can check that if you act the symmetry operator U over there on either of these ground states. Well, we can first use that for all the qubits away from this x equals 0 line. In the ground state subspace, the poly x operator is equal to 1, right? So I don't have to care about any of the poly x operators outside of the x equals 0 sites. So I only get a product over these operators. Okay? And because of this Ising term, we know that this will not be an eigenstate of this operator here. So this will have a non-trivial action within the ground state subspace, and that's precisely what we mean by spontaneous symmetry breaking. So this defect correctly spontaneously breaks the Z2 symmetry only along this localized line. Okay, so we have inserted an interesting defect into our paramagnet FPT. Now let's gauge the Z2 symmetry and see what we get. So now if we gauge the Z2 symmetry in this defect Hamiltonian, well, I'm not going to go through all the gauging steps. We'll go through a lot of gauging steps in a moment. But if you do exactly what Carolyn taught us to do in her lecture, this is what you'll get. So the Hilbert space will be the same Hilbert space as over there. And now the Hamiltonian will be the following. So all the terms in HP will still go to this Hamiltonian here. But then you'll have a change hopefully that's clear. So now we remove the star terms that belong to the sites where the defect goes through. And we replace those star terms with a single Z operator. And this notation here means that this is the poly operator that acts on the link that goes from 0, y, that's the 0, y, and goes in the y direction. So it acts on this link. Good, so as we expected, if we gauged the symmetry of an SPT with a defect inserted, we got Z2 gauge theory with a defect inserted.
So, what's the coordinate of Z in the equation?
Right here?
Yeah.
It is acting on the qubit on the link that goes from the site 0, y to 0, y plus 1. And this notation here means I look at the site 0, y and I connect, I look at the edge that connects the site in the y direction to that initial site. Okay.
So I can ask you a question.
Yes, please.
So if you were to take the defect C2 gauge theory and found this defect and it'd be equivalent.
Sorry, what defect is E2 gauge theory?
I'm basically asking if this commutes. So like, on the one hand, you can take the defect in the pre-gauge and then gauge.
Uh-huh.
And on the other hand, I'm asking, can you gauge and then find this defect naturally using, like, by finding a Z2 symmetry?
So we'll basically answer your question in a bit. So we'll see how to insert the defect starting from Z2 gauge theory instead of doing it before gauging. Yeah. Okay, so this defect has a name. In the exact model we have right now with this exact Hilbert space, I don't know what to call it. But if you go into the low energy space, so this defect becomes what people call a condensation defect. At low energies, where that Z operator over there, going from site Y to the site right above it, is equal to 1. So in that low energy subspace, this defect becomes a condensation defect. Okay, so what is the word condensation defect? Well, there's two perspectives. One is if you're used to string operators in models of topological orders, what we've basically done is we just added the E anion string operator, right? So we've basically said, I'm going to choose a line, remove all the star terms, add the E string operators along that line, and I'll condense the E anions along that line, right? So that's one perspective. So this defect basically condenses the E anions at the x equals 0 line. A more symmetry perspective is that it eats one of the one-form symmetry operators. So it eats. Maybe eats isn't a good word because we're right before lunch and I don't want anyone to get too hungry, but it eats the topological, I'm going to use the terminology I introduced last lecture, the topological Z2 one-form symmetry, which is generated by this product of Z operators along some one cycle. Okay. If you recall from last tutorial and from some of the previous lectures, the Z2 gauge theory has this as a symmetry, and it's a topological one-form symmetry because I'm enforcing the plaquette to equal 1, the plaquette operator to equal 1 in all the states of my Hilbert space. Okay, so yes?
Is defect topological or not?
The condensation defect?
Yeah.
Yes, I'll write that in a second.
Okay.
Okay, so what do I mean by it eats the Z2 one-form symmetry operator? So here's a picture of space, and my square lattice is going to be on this space. And suppose I had, get a color. Suppose I've inserted my defect right here along this line. This is my x equals 0, line where my defect is inserted. And then suppose I had this one-form symmetry operator, and I wanted to act on a state, and I wanted to act along this loop gamma, right? Well, what can I do? Well, step one, I can use the fact it's topological to then move gamma. So I'm going to move gamma. Okay, the space didn't shrink. I'm just not good at drawing. So I'm going to move gamma exactly to where the defect is. So now I have the one-form symmetry operator acting exactly on the line where the defect is. But now nothing happens on the full Hilbert space. It's just chilling, right? So now if I go to low energies though, so I go to low enough energies where Z is always equal to 1, now this one-form symmetry operator, when it acts on this line, is literally equal to 1 as an operator. Good. So that's what I mean by eating. Okay. And from this eating, we can actually see this defect is a non-invertible defect, right? Okay, why is that? Well, suppose I said, oh, this is the configuration I get after I acted the one-form symmetry operator into this defect. We say, oh, I know what operator you must have started with. You must have started with the W operator. And I would say, yes, that's one possibility. But maybe I started with the operator equals 1, right? So I don't know what operator I started with. There's no inverse to this process. So it's non-revertible. Okay, and then there's a great question. Is this a topological defect? And the answer is yes. So what does it mean to be a topological defect on the lattice? It means there exists some unitary operator that moves it around, right? The location doesn't affect the spectrum. The operator that moves it around is a bit complicated, so I'm going to cop out and just tell you which paper you should look at to see it. It's a paper by Nat Kantivasa-Dekaran. And Xia Chen from, I think, 2 years ago. Okay, good. Okay, good. Okay, good. So we saw one perspective of how to get a condensation defect. There's one way to get a condensation defect by inserting some defects before we gauge. You get some new defects after you gauge, and that could be a condensation defect. This picture of inserting defects before gauging is super, super general. So you can get all different types of symmetries and defects by inserting things before gauging and then gauging. But there.
Is it a topological operator for some non-invertible symmetry? This condensation defect.
Good question. So the defect here is codimension 1 in space. So as an operator, it will be a zero-form operator acting everywhere in space. So it doesn't really make sense to call a zero-form symmetry operator topological. Yeah. But we'll write down the operator corresponding to this defect later on.
Can you recover all the condensation defects in toric code in this way? Something to paramagnet or whatever it was, HP kind of defect?
So there's 5 non-trivial condensation defects in the ground states of toric code. I know how to get 2 of them doing this. But one way to recover all of them is to do what I'm going to introduce next, which is called higher gauging.
And those two that you know are SC and SM, like both condensing animals.
The 2 I know is condensing E on a line and condensing F on a line. I know how to do that before, but there may be ways to do the other 3 non-trivial ones. I just don't know off the top of my head. Yes.
So, do we think it exists? Like it should be like surjective. I can reach every surface in the post-gauge theory from pre-gauge theory. We think it's true.
I don't know if that's true.
Okay.
Yeah, I don't know if it's surjective or not. It probably is if you're being general enough to consider continuous symmetries. It probably isn't. Any other questions? Good.
If there is a unitary operator to move this defect along
Yeah.
the lines, do we require this operator for it to be topological?
Good. No, it should not. The unitary operator that moves the defect, right? It should not commute with the Hamiltonian, right? So what is the defect? The defect's a modification of the Hamiltonian. I should be able to say, oh, the defect is right here when I look at the Hamiltonian. I should be able to apply a unitary operator and move the defect to like over here. And the Hamiltonian should look different. The Hamiltonian should be modified in different places. But the key point is because they're related by unitaries, the spectrum of these Hamiltonians are the same. So if I just give you a bunch of ED data, you would never know where the defect is. Any other questions? Cool. Okay, let's get into higher gauging. So this condensation defect can be inserted. So by inserted, I mean I could start off with this Hamiltonian, the gauged Hamiltonian, and then insert it into the Hamiltonian without doing this gauging step. I can insert it by what's called higher gauging. So what is higher gauging? Maybe I'll go over here. So what is higher gauging? Well, normally when we gauge a symmetry, we gauge it everywhere in space. Or from a space-time perspective, if I'm going to discrete gauge, normally when I gauge a symmetry, I sum over topological defects over all of space-time. But higher gauging is the machine of only summing over topological defects in a submanifold of space-time. Or from a lattice perspective, I'm only going to gauge the symmetry in a subspace of space. Okay. Good. Oh, actually, I changed my notes slightly. By popular demand, I'm going to gauge the Z2 one-form symmetry normally first. This isn't for the higher gauging. We're just going to do this for the love of the game. Okay. 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 Sorry. I swiped down my notes and I got totally confused. Let me finish my spiel about higher gauging generally. Good. So higher gauging is we're going to be gauging. So sometimes people use the word Q gauging. Q gauging is gauging some higher form symmetry in a codimension Q subspace. Okay. So zero gauging is ordinary gauging. I gauge it everywhere, right? And you can quickly see that, you know, I can only higher gauge if I have a higher form symmetry. And the nice thing about, well, one important thing about condensation defects is that they're topological defects that can end and remain to be topological. So like normally when I have a topological defect line, like this loop, it can move wherever. But if I wanted to have it end on some like zero-dimensional things, I usually can't move those zero-dimensional things, but I can still wiggle the loop. Condensation defects, I can have them end on lower-dimensional things, and the whole thing is still topological. I mean, you can kind of easily see this from what we did over here. Up here, I inserted the Z2 SSB defect on this whole line. I could have just inserted it on a few links and had it end, and I would have gotten the same types of condensation defects. Okay. And I actually think it's probably a good invariant definition of condensation defects. If I have a topological defect that can end, I think that's a good definition of condensation defect. It isn't based on some construction, which is nice. It's really some invariant thing. Okay. Okay, now we're gonna, so we're gonna do a warm-up. We're going to do a warm-up and we're going to gauge the Z2 one-form symmetry generated by the W operator I wrote on the left over there. Just normally, we're going to zero gauge it. So step one is going to be the same style of steps that Carolyn taught us in her lectures. So if I want to gauge a symmetry, step one, I should introduce new degrees of freedom. And these kind of are like the gauge fields. Okay. So here I'm going to introduce a qubit on each lattice site. Yes. I'm going to denote their Pauli operators by putting tildes. So the Pauli operators that act on the new qubit at site S are those guys. And you know, you may ask, well, why am I putting on the sites? Is there some rationale behind it? Honestly, I don't really think it matters all that much where you put these extra degrees of freedom. I could have put them on the links. I don't think it really matters. One rationale for why you may want to put it on the sites is because a site is dual to a plaquette, and a one-form symmetry's gauge field is a two-form. But I really don't think it matters. You could put it on the links and everything would be fine. You just get a model where things are on links instead of sites. It may mess up some crystalline symmetries, but modulo stuff like that, I don't think it makes that big of a difference. Okay, so what happens? So what, you know, when I say I introduce a qubit, what do I really do? I have a new Hilbert space. So I take my old Hilbert space that I wrote down over there on the right-hand side of the board, just to be super, super clear. This is the Hilbert space I'm going to consider now. I'm not going to put down a check. So this is banned. We're not going to use that anymore. Okay, so I replace my Z2 gauge theory Hilbert space with a bigger Hilbert space. with qubits on every site. Okay, I'm going to call this h big. This is big. Okay, that's step 1. Step 2, I need to enforce the Gauss law. And enforcing the Gauss law includes defining the Gauss law. So I'm going to define this Gauss law. It's going to be, for any edge E, I want this operator to equal 1 on my Hilbert space. It's going to be a Z acting on the edge, and Z tilde is acting on the sites. So I wrote this for a horizontal edge, but please note this is also true for a vertical edge. So when I introduce the Gauss law, what do? Well, once again, I modify the Hilbert space. I now have H big, and I'm going to say I only consider the states for which G equals. So I take H big, and now I replace it with H big modulo all the states where G is equal to 1. And I kind of think choosing a Gauss law is an art form. There's many choices of Gauss laws. There's many inequivalent ways to gauge a symmetry. One thing Gauss law should do, at least for invertible abelian symmetries, is they should trivialize the symmetry operator you're gauging. Right? Gauging a symmetry should get rid of the global symmetry. And indeed, this Gauss law does that job. Make sure everyone can see. My symmetry operator, W of gamma, for any gamma, can always be written as a product of the GE operators. This is true on any Hilbert space. I don't have to use the Gauss law to do this. But now I do use the Gauss law. Let's see, let's call this, oh, I wrote 1. This should have been like H check. Sorry. Yeah, so I started with my H big, enforced the Gauss law, and now I have the Hilbert space of my gauged model, which I denote as H check. Good, so this Gauss law and this gauging procedure, of which qubits we used, trivializes the symmetry operator in my gauged model's Hilbert space. So that's a check, it does it. Okay, and then step 3. We want to next minimally couple. And again, the point of minimally coupling is, if I had an operator that was symmetric before gauging, it should survive gauging, right? So it should be gauge invariant and should commute with the Gauss law. But I need to modify it in order for it to commute with the Gauss law typically. So I'm only going to care about the operators that are inside the Z2 gauge theory Hamiltonian. They're all the A, the star operator is A. And minimal coupling will be, I take my A, and I'm going to replace it with X tilde acting on the same S times A. Okay. Why do I do that? Well, the Gauss operator over there has a Z, a lone Z in it. So it certainly doesn't commute with the AS operators without modifying them. But when I modify AS in this way, with an X tilde right there, now this new operator commutes with all of the Gauss operators. Okay, so now I have a modified Hamiltonian, H minimally coupled, and it looks like this. Okay, good. And we could call it a day. Like, I started off with my Hamiltonian, I did my 3 steps, I introduced the new degrees of freedom, I enforced the Gauss law, I'm minimally coupled, I have my Hilbert space, H check over there, I have my new Hamiltonian, we could be done. But this doesn't look at all like the theory up, where'd it go? The theory up there with the condensation defect. Did we mess up? No, not necessarily. Maybe we just have to choose a different basis, right? And that's exactly what the case is. So now the last step is I'm going to do a unitary transformation. Do a unitary transformation where the X tilde operator gets sent to x tilde times as. The x operator on an edge doesn't change. The z tilde for a site does not change. And now the z operator for an edge does change. It becomes the Gauss operator. You can check this is implemented by a unitary transformation and is locality preserving. It should be viewed as a basis change. And now when I go to this new basis, something quite nice happens. In this new basis, now the Gauss law, GE equals 1, after the unitary transformation becomes ZE equals 1. So all the qubits that I started off on the links are now just polarized. They're all pointing spin up. I can just forget about them. Okay? And when I forget about them, my Hilbert space in this new basis, H check, is just a tensor product space. Okay? And my Hamiltonian, H minimally coupled, what does it become after I gauge? Well, A's are made out of X's. X's don't change. X tildes get modified by an A, and A squared equals 1. So the A goes away. Okay. So I get back the paramagnet I started with, right? So we saw that if I started with the paramagnet and I gauged the Z2 symmetry, I got the Z2 gauge theory. And it had a new Z2 one-form symmetry. And if I gauge the Z2 one-form symmetry, I returned back to the paramagnet I started with. Okay, excellent. Okay, so that was gauging the one-form symmetry everywhere in space. You could call it zero gauging. Now I want to higher gauge the one-form symmetry. Yes, please.
If there was an anomaly, which step would it show up?
So one way the anomaly will manifest in this procedure is you will find that the Gauss laws, you can't all enforce them to equal 1. So for example, the Gauss operators, they may anti-commute. If they anti-commute, you can't all set them to be equals to 1. So you kind of end up with a model that has 0 states. So there's something terrible that went wrong. Good question.
Are you suggesting that this condensation defect is just the background gauge field for the one-form symmetry?
No.
No.
Okay, so now let's higher gauge. So we're going to one gauge the one-form symmetry. And we're going to gauge it along the same line up there that we inserted the defect. So at x equals 0. I'll call that line gamma sub y. Okay. So same steps. Let me go through them a little bit quicker. Step 1, introduce new qubits. Why qubits? Why not some other crazy degree of freedom? Well, it's a Z2 symmetry, so I really only need to have a 2-level system because there's only 2 group elements. So I'm going to introduce new qubits, and I'm going to introduce them on the vertical edges, connecting a site 0, y to the site 0, y plus 1. So on all the vertical edges where the defect lives, that's where the new qubits are going to live. There are no new qubits over here, for example. Okay, that's important. So we already see a big departure from ordinary gauging. We're not putting qubits everywhere, only along the defect we want to insert. Okay. So again, now I have an H-big Hilbert space with additional qubits on this line. Yes?
Why in the edges instead of
It doesn't matter. I kind of have the benefit of already seeing what would happen if you put it on the sites instead, for example. And you just get the same model that I erased over there, but now there's like some qubits on sites instead of links. So it's just for aesthetics. So step 2 is going to enforce a Gauss law. And the Gauss law I'm going to choose is going to be defined with a y coordinate. So if this is the site 0, y, the Gauss law is going to be the following. Okay. So remember, on the vertical links of along this row, there's 2 qubits per site now. Per edge. There's a qubits on every edge I started with, and there's a new qubits I just introduced. And now this Gauss operator is going to act by z on one of these qubits, and act by x's on the new qubits I just introduced. So that's the Gauss law. Okay, why do I want that Gauss law? Well, I don't want to trivialize the symmetry operator away from that line. Okay, I didn't even add new degrees of freedom, so I'm not going to do that. But I do want to trivialize the one-form symmetry operator exactly at this line. Okay. And now, the one-form symmetry acting on this line gamma y, which remember is the x equals 0 line, I can rewrite it as a product of these gy operators, and that's equal to 1 on the gauge invariant Hilbert space. Okay, good, that was step 2. What's step 3? Minimal couple. Okay. So, the plaquette operator commutes with this Gauss operator. We don't need to do anything. But again, the star operator does not commute with this Gauss operator. Now we need to modify it. And this time we'll only be modifying the star operators belonging to the sites along this row. And now they'll become something like this. So they still act x on all the sites, all the edges touching the site, but now it'll also act z tilde on this bottom site. And you can tell that will commute with this Gauss operator. Good, so we have the minimally coupled Hamiltonian. It'll be the star operator, the normal star operator, and every site away from the defect. But for the sites along this row where the defect is going to be inserted, now it's this modified star operator with an x tilde down here. Okay. Good, and that's it. We could declare victory here. We have the gauged model. But it doesn't look at all like the Hamiltonian we had before. Right? So let's find a new basis. Okay, this basis transformation is a little bit more involved, but I think it's good for your soul to see it. So I'm only going to be modifying the operators near this row. For the z tilde operator on a vertical edge, I'm going to have it be modified to this. Okay, what else? For this z on this horizontal edge, I'm going to have it get modified to this. So now there's an x tilde acting down here. For the z on this horizontal edge, I'm going to have it get modified to this. So it's just like this, but now the x tilde goes to the right instead of the left. And for a z acting on a vertical link, I'll have it go to this. Okay. So every site here is always going to be at x equals 0. And all other operators are not being changed by this unitary. I'm only writing the operators that do transform into this unitary operator. So, in this new basis, you can check that The BP operator is unchanged. So now the Gauss operator is changed. Now the Gauss operator is changed. And now the Gauss operator gy, it goes to z at the length from 0, y to 0, y plus 1, and that should equal 1. Okay. So what's my total Hilbert space? Remember I had qubits on every edge. I had a special column of edges where there's 2 qubits. Now one of those qubits are totally polarized, so I can forget about them. So again, I have a Hilbert space with only one qubit on each edge. Okay. But now if I enforce this Gauss law, it modifies the plaquette operator. Remember, the plaquette operator was a product of z's around a plaquette, and it was this z, not the tilde z. It was this z. So now I have a modified plaquette operator. Or b tilde, here's a compact way to write it. 1 minus delta x equals 0. So for the plaquette P, if I call this the x position of this lattice site, this is only here if x is not equal to 0. And then I have a z on the right-hand side, which is only there if x is not equal to minus 1. Okay. So for the plaquette operators, away from the defect, they look normal. But if I have a plaquette operator that touches the defect, it's missing one of the edges. Good. Okay, so now I can write down the Hamiltonian. And if I drop the tildes on the z and x operators I introduced, and just call them normal z, normal x, now my Hamiltonian looks like this. So I have all the normal star operators away from this row. And I have the z's along this row. Okay. But crucially, the plaquette operators are modified. Okay. So the Hamiltonian is the same Hamiltonians we got before. The Hilbert space is different. And the Hilbert space is different because the plaquette operators have been modified when we did the one gauging procedure. So now if I take my one-form symmetry operator, W, now I can use the plaquette operator to start to move it. Right? I'm using these plaquette operators to move it to the right. And eventually I'm going to get the W that acts like one lattice space to the left, for example, of the defect. And now I use these modified plaquette operators. And that will kill it. That will have the operator equal 1. So now I don't have to do any low energy limits stuff. Now just by moving the symmetry operator into where the defect is inserted, I can have it be even. Okay, so I have about a minute left. Let me skip talking about the operator version of the condensation defect. I'll find a way to have the notes be uploaded. So you can always view it there. And to be honest, the operator version looks just like the version that's already written in papers in field theory context anyways. So it's really not that different. But let me summarize all the different condensation defects in this model. Make a table here. Okay, so there are 5 non-trivial condensation defects, in this model if you go to the ground state subspace. So you go to the subspace where all of the star operators are equal to 1. Okay. So there's an E condensation defect. There's an M. There's an E times M. There's what sometimes people call EM. There's sometimes what people call ME. So you can build all of these by higher gauging. So what is it that you higher gauge? For the E condensation defect, well, that's what we just built, right? So what do I higher gauge there? I higher gauge the Z2 one-form symmetry associated to the electric operator, the Wilson operator. So the product of Z guy. Okay. For the M condensation defect, I haven't talked about it, but Carolyn mentioned it, that there's another one-form symmetry. It's built out of X's. So for the one-form symmetry guy, the M condensation defect, the one-form symmetry is the one built out of product of X's along the loop. Now the other two, the E times M, that's like condensing the fermion of the tor code along the loop. And you do that by higher gauging the diagonal of these two Z2 one-form symmetries. And there's two other ones. EM, you just gauge the entire Z2 times Z2 one-form symmetry group along this line. And the ME, turns out there's an inequivalent way to gauge this. So you do what sometimes people call twisted gauging. There's an inequivalent way to one gauge this, to gauge the Z2 times Z2 along this loop, along this line. Okay, so which of these defects are invertible or non-invertible? We saw the E condensation defect was non-invertible, and that's true for all but one. The defect that condenses the F anion along the line, that's actually an invertible defect. And then the symmetry transformation. What does E do? Well, we saw that when I took E and I pushed it into the wall, it absorbed it, right? So E could get sent to 1, but I could also have it be absorbed and unabsorb an E on the other side and keep on pushing it through. So E gets sent to 1 or E. M has a similar transformation. I won't write them all, but one that is nice is this, the invertible guy, it sends E to M, and it sends M to E. Okay, so it does the EM exchange permutations. Cool. Yes. So I went a little bit over time, sorry about that, but if anyone has any other questions, yeah, please ask. Thanks.
So, I mean, at least I can imagine taking the defects out because it's built for condensing one plus
Yeah.
I can imagine at least theoretically trying to expand it on a slab or a strip in space-time, and inside that strip results in the all zero gauge. Is it a nice way on the lattice to just kind of build a slab out of the defect to expand it a higher dimension, to go from whatever one gauging, whatever to zero gauging. So I'm just imagining, it's like a network. And just
Yeah. Yeah, it's related to this thing where if I take duality defects and infuse them, I usually get a condensation defect out of that. I haven't seen it on the lattice. So to be honest, I don't think anything is in the literature that I wrote about. I tried to really make it into a version that's similar in field theory.
Okay, that was going to be another one of my questions actually.
Oh yeah. Yeah, so the paper, I think a lot of times when people are on the lattice and talking about condensation defects, there's either two perspectives. One is tensor networks, and it's very elegant, but it's kind of hard for me at least to rephrase it in field theory language. Or it's more information theory, you're only looking at states, for example. So both of those are kind of hard for me to translate. So I tried to write it and use the same words as field theory. So.
Sorry, what was the question?
So I think the question was, is there a way to take this defect on the lattice and open it up and have two defects?
Yeah, two Yeah, so basically like take this defect, kind of open it up, so that the central part is kind of what if the SPT, maybe the paramagnet in your language, and then the external parts are, the core code.
You can certainly take like the model and just only gauge the Z2 one form symmetry in this like thicker slab, and I just haven't checked if you like slap these together, you'll get like exactly this defect.
I think at least the fusion and the separation should kind of.
Yeah, because they're topological, definitely. Jared.
Yeah, if you have these symmetries with open boundary conditions, can you still do this staging? Like, what happens at the boundaries when you try to trivialize the symmetry?
Good. So everything I did was a square lattice with periodic boundary conditions. Now you're asking, what if I have an open boundary? Well, I think it depends on what the open boundary condition is. So if it's smooth versus rough. But if you choose so everything was topological one-form symmetries. So if you choose a boundary that doesn't condense the one-form symmetry you're asking about, I don't see any issues with one gauging. But if you have like the rough boundary, for this example, you can always just take this operator and just push it into the rough boundary and get rid of it anyway. So it doesn't really make sense to one gauge that.
Okay. But like, I guess even in the zero form symmetry case, like gauging that with open boundaries, is it still like, yeah, like, does that still work the same way as this?
Yeah, so I mean, when I gauge a symmetry with open boundaries, I just have to make sure that you just are a little bit careful near the boundaries. Like maybe the Gauss operator is different near the boundary, stuff like that. But you can certainly still gauge, and like it's very standard. Like if I gauge a symmetry in the bulk and I have a boundary, after gauging I'll have the symmetry kind of still live on the boundary. Yeah, so this is kind of like the what do people call it? Like the asymptotic symmetries of gauge theories, but this is, the boundary isn't at asymptotic infinity, it's like in front of you.
Oh, yeah.
Yeah.
So this is actually just a simple one to check something.
Uh-huh.
So E goes to 1 or E, you said, under SE surface.
Yeah.
And so can I think of that as, I've got the defect along one of the cycles of this torus. I can have a line of Z operators parallel to it on the left.
Uh-huh.
And that state is equal to the state on the other side with ones or Zs. Is that the statement? Like, how do I interpret that as one state equals one state?
I wasn't thinking of it at a state level, I was thinking of it as an operator level.
Right. So
I
actually misspoke. I meant to say one operator equals
Uh-huh. Yeah, so here, oh, I didn't write the plus, I'm sorry. It's going too fast. Yeah, sorry. I hope that didn't cause any confusion.
So on the right, it would be like the operator 1 plus Z on each link.
So in this case, so here I took W, I push it to the defect. And it's like, oh, I take like my W line, I push on the defect, I get 1. But here's something else I can do. I could push W, push into the defect, it equals 1, but I don't tell anyone that it equals 1. I then say, oh, well 1 is also equal to the W to the right. Because I could have also took a W from the right and pushed it. So if I don't tell anyone I do that middle step, it looks like I take W, just push it straight through, and no one notices anything. So that's kind of what my interpretation of this result is when you're talking about the operators.
I see.
I could take E, push it through, so I could get 1 or I could get E.
Yeah. And in the field theory perspective, I think you drag out a twisted sector, right? So can you see that here?
Yeah, so in the field theory perspective, now this defect is extended in time. So in the field theory perspective, I have a surface. And I've summed over the topological defect lines on this surface. And we do the transformation by taking, I'll write it right here, by taking my E line, wrapping this surface around it, and then swooshing this, the surface. And when I do that, then I should get 1 plus E. Then I get this non-simple object.
Other questions, comments? No? Okay, so let's thank Lord.